today, but my goal is really to move on to bigger and better things. The way that we present mesh analysis is a little bit different than the way that we presented nodal analysis, and that was sort of intentional. I hope that you watched the video, and I hope that you saw that there's tons of similarities and parallels between mesh and nodal analysis. And so we're not going to go through mesh in the same level of detail that we did for nodal. It'll probably come back up when we start talking about some homework questions, and there's maybe one or two things that you might have to refer to the book for, but I mean, to go through mesh analysis in the same level of detail that we did nodal would be like a whole other 2.5 week, would be a whole other 2.5 week process, and I'm not really, haven't really built that into the schedule. So, really quickly, what was mesh analysis? Can anybody answer that question for me? How is it similar? How does it differ from nodal analysis? First things first is it's really, it achieves the same purpose, right? It allows us to solve a circuit for its state. It may be a little bit different in the exact values that it gives us, but it replaces a lot of the techniques that we learned in Chapter 2, or provides an alternative to a lot of those techniques we learned in Chapter 2. What are the main differences? Yeah.
Do an impedance matrix instead of an admittance matrix?
It's a very good one, yeah. We're working with an impedance matrix instead of an admittance. And that has to do with this basic linear algebraic equation that we're working with. In nodal analysis, we're dealing with I equals Y times V, where these two are known, and so we're solving for V. Over here, these two are known. Our voltages and our impedances are known, and we're solving for I. So the basic difference has to do with KCL versus KVL. Nodal analysis is that's a Z. That's for impedance matrix. So the basic difference between nodal and mesh analysis is one is based on the use of KCL, Kirchhoff's current law, and the other one is based off of KVL, Kirchhoff's voltage law. And so when we are using KCL, when we're using nodal analysis, we're solving for the voltages at the nodes. And when we're doing KVL, when we're doing mesh analysis, we're using Kirchhoff's voltage law, and we're solving for these loop currents that we have to define. So the mesh analysis problem that we went over was this one here. If you haven't taken a look at it yet, it's not too late, obviously, but we'll be doing a little bit more with that today, but you definitely do need to go back and take a look at this, this introduction to mesh analysis. So the main takeaways here, when we're defining a mesh analysis problem, we have to define these loops. There's lots of different ways that we can define these loops. These are not the only two that exist. We could have IA, where it is shown, and IB circling the whole exterior of the circuit. Right? The only requirements we have for the loops are, well, they can't be the same loop. They must complete a full circuit, meaning that they must start from one point and come back to that same point. And they can't pass through the same branch twice. So you can't do a figure 8 type thing where, let's say, IB crosses through R3 2 times. So we define the number of loops that we need, which in this case is 2. There's an equation for it, which is the number of branches minus the number of nodes plus 1. We have 7 branches, 6 nodes. So 7 minus 6 plus 1 equals 2. If you watch the video that I posted online, you'll also see I referred to something called the Windowpane Method, which more or less just says if you look at the circuit like a bunch of window panes, then you can kind of tell, right, there's 2 squares there, and so there's 2 loops that we need to define. That method works under most cases. I really just used it as a check to check the number that I get from B minus N plus 1. So the rest of this, I'm not going to go through in detail. Essentially, we define the KVL for the circuit for loops A and B. We do the same substitutions that we've seen in the past. We're going to substitute for Ohm's law, which is going to give us our voltages as a current times a resistance. Now, the currents we're going to be using initially are going to be I34, I45. We need to translate those into the loop currents that we defined initially. Those loop currents, for most of the branches, are very easy. So the current flowing here is simply IA. The current flowing here is simply IB. Okay, the only branch that is affected by two of the loop currents is the one in the middle, right? So the one in the middle, which is R3, that one has IA as well as IB flowing through it. And so I use this example here to show how to handle it. So I25, the current flowing from here to here, if we wanted to put that in terms of IA and IB, we would simply take the sum of the two, taking into account the direction. So I25 has the same direction as IA, so it'll be equal to IA and then minus IB because IB is flowing in the other direction. So when we're doing this mesh analysis, those are the two substitutions that we need to make. One substitution is based off of Ohm's law, where we replace the voltages across the branches with I times R. Those currents will be defined most likely I12, I23, I34, the way that they're labeled on the first diagram. And the second substitution you have to do is to put them in terms of the loop currents, because that's what you're going to be solving for. So as we get closer to the end of this problem, we're going to group the loops. We're going to group the equation by the loop current. So essentially we're going to extract all the coefficients of IA, extract all the coefficients of IB, and that will give us the ability to put this into a matrix form as shown here, where we have IA, IB, the coefficients of IA and IB. This is the impedance matrix that we were talking about. And then we have the independent voltage sources that are present in those loops. Is that where the video left off? Oh, okay. I thought I went over the inspection method. I guess not. All right. So, moving on. Okay, so the next question we're going to ask is what different cases exist? Very similar to the way that we parsed through this for nodal analysis, right? We had nodal analysis. The base case was just independent current sources. That was not necessarily even really the easiest one to do, but it was the starting point. It was how we defined our by inspection method, and then we branched out into others. So for mesh analysis, the base case is going to be where we have independent voltage sources only. All right. And the reason for that is because, these sources may be easily represented in KVL. Same reason why we started with the circuit with only independent current sources for nodal analysis, because it's based on KCL and independent current sources are easy to represent in KCL. This is going to be the basis, spelled that wrong, for a bi-inspection method. If we go back and take a look at this here, I can explain the bi-inspection method pretty easily. It works in a way that's very similar to what we saw for nodal analysis. Again, your diagonal elements are positive, your off-diagonal elements are negative. Your diagonal elements are more likely to have more than one component. Your off-diagonal elements are more likely to just be one. And the way that it works is, for loop A, our diagonal value is all the resistances that are on that loop. So R1 plus R2 plus R3. That's what we have down here. For our element 2, which is associated with loop B, it's all of our, again, our adjacent resistors, which are R3 plus R4 plus R5. That's what you have down here. And then these are minus whatever the resistance is that's shared by the two loops. Similar how in nodal analysis it was minus the admittance that traversed the two nodes. So R3 is the middle branch, and so we see that there. These represent our independent voltage sources that are shown. And so if you have a good understanding of how to do bi-inspection method for nodal, it's just a different flavor on that. So my hope is today we'll be completely done with mesh analysis, and that will be done essentially with everything that's going to be required knowledge for the midterm, which will give us a full week to do any review and for you all to ask questions. Okay. So dependent voltage sources, these can still be represented within KVL, so we can still build our equations in the same way. This is going to prevent us from using bi-inspection. So we're going to have to rely on the equations themselves. Again, the exact same thing we saw when we went from independent current sources to dependent current sources for nodal analysis. Okay, so for this one I'm going to draw a little picture. If we have a circuit that looks like this, and let's say we're trying to run mesh analysis on this. So this is VS, this is IS. The other values aren't really important. So if I'm trying to perform mesh analysis on this circuit, one of the first things that I would do is I would define the loop current, right? So let's say I did that. Normally, we would have to solve for both IA and IB. What do we see about this right here? Do we still have to solve for both IA and IB? Yes? No? No, and why is that?
Because it's already defined by IS.
Right. IA is equal to IS, which is equal to a known value that's given to us. So this will what do I mean such that the source is isolated? So I said when you have an independent current source in your circuit, make sure to choose your loops such that the source is isolated. Another way that we could have done this is I could define IB like that. Okay, if I did that, it would change the relationship because now it would no longer be IA is equal to IS. It would actually be IA plus IB is equal to IS, right? Because we have two loops flowing through that branch. Nothing wrong with doing it that way, but hopefully you can see it inherently just adds another equation that you have to solve for that you wouldn't have otherwise. So it makes more sense in this case to define it as such. And this is similar to, again, when we had independent voltage sources for nodal analysis, we said try to define your reference node such that the independent voltage source is between a non-reference and a reference node, because those are the quote-unquote best cases because they just eliminate a variable that you have to solve for. Okay, and then with dependent current sources, and so for this, if we have a circuit which looks like this, I don't really care what the rest of the circuit looks like. Okay, that's equal to alpha times Vx. But we're not going to be able to define KVL for that loop that IA is flowing through. Therefore, what we're going to end up with is using that expression right there. The dependent current source itself will define how IA is in turn defined. And then you'd have to just integrate that with the other equations that you have. Yeah. There are more examples in the book that we're not going to be going over. If you have questions about specific parts, I recommend that you take a look at it. I'm hoping that most of you will be able to kind of connect the dots after we spend so much time doing nodal analysis, that this will come a little bit easier. Okay, so we are going to go through one example of mesh analysis with dependent current sources. But I think that's going to be the end of what we do for mesh analysis. Let me check. Yeah. But this makes sense because it is one of the more, let's say, confusing cases of how to treat these. All right, so our circuit looks like this. As promised, dependent current source has a value of Vx divided by 2000. And this one's, it's a bigger one. So this is a good final example to go through because it definitely represents one of the more difficult versions of this problem that you could see. Okay, so this is, it's a current source, 2 milliamps. This is 3 volts. We have 4,000 ohms, so 4 kilo ohms, 6 kilo ohms. We have 2 kilo ohms. This is our Vx right here. And I think that's it. All right, so step number 1 is going to be to label the circuit. So let's see here. I'll try to use the same. This is node 1. I think I called this 2, 3, and 4. Like usual, we will be able to call this I13, et cetera, et cetera. Vx, another name for that would be V34, right? That would be the same thing. All right. Next, defining our loops. So the first thing we're going to be looking out for when we define our loops is always going to be that elusive independent current source, right? Because that is like free money. We can get something for nothing. We do have an independent current source. And so the only thing that we need to make sure to do is that for that branch only, we want to have one loop current flowing through it. So what I'll do is I'll define this right here as IA. We don't care if there's another current flowing through here, another current flowing through here, we just can't have anything else passing through that branch. And that will automatically reduce our problem to by one variable. One thing we forgot to do is we can use the b minus n plus 1 equation to tell us how many loops we're going to need. If we use the Windowpane method, what does that tell us? Yep, 3, right? But we'll go ahead and do it the other way. So the branches, 1, 2, 3, 4, 5, 6. So 6 minus 4 plus 1, 3. All right. Say it again.
How many branches?
6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Now what about placing some of the other loops? Look, 99% of the time, most people just go ahead and draw them like that anyway. They just throw them in the middle of the window panes and move forward. There are cases where using bigger loops can be better. For example, using one loop that encompasses, the whole circuit. I'm not going to go into why that is, but for this case, it kind of works out because it makes most sense to use those smaller loops. Again, it's good here to only have one loop passing through that dependent current source, or else what we would have to, right? It's going to be easier if we have the case IB equals Vx divided by 2000, as opposed to IB plus IC equals Vx over 2000. It's just an unnecessary, again, making equations that can be simple, making them more complex. And then I'll just go ahead and define IC like that. All right. So next. So let's write out the equations that we need. To begin with, I'm going to go ahead and still assume that we have 3. One of them is going to go away, but so the first one for A is going to be IA is equal to 2 milliamps, right? That's an easy one. For B, we will have IB is equal to Vx divided by 2,000. And then for C, this is really the only one where we're going to have to apply KVL. And so what I'm going to do is write that out. So we will have 3 volts minus V31 minus V12 equals 0. Now, why are the signs as such? And here we're starting to skip steps a little bit. If I were to draw out V31, that would have a sign polarity that looks like that. And if I were to draw out V12, I would have a polarity that looked like this. So both of those polarities oppose that of the 3 volts. If I wanted to, I could have written it like that. Again, we have lots of different ways of writing these equations. You can always play around with the signs. You just have to be cognizant of why you're doing it. Okay, so right off the bat, we can see that that's going to go away. Well, it's not necessarily going to go away. We're still going to use the value for IA, but we're not going to need to solve for it. So now we're going to have 2 unknowns we're going to be solving for. And that's going to be related to this equation here and this equation down here. So those are the 2 that we're going to have to work with. All right, so next, we're going to make substitutions until only the independent sources, the resistances, and the loop currents are left, right? Because that's the end point that we're trying to get to. When we have the linear algebraic form of this and we solve, we're going to have the independent sources, whatever values they are, we'll have the resistances, and we'll have the loop currents. We don't want to have anything like an I12 or V12 left in the equations that they don't have a place in the final form. All right, so let's look at this. So we have IB equals Vx divided by 2,000. Obviously, Vx is not an independent source. It's not a resistance, and it's not one of the loop currents. So we'll make a substitution for that. That's equal to V34 divided by 2,000, which is the same as I34. So let's break this down for a second. So V34, what does that equal to? It's equal to I34 times 4,000. right? Because I34 is the current running across this branch from right to left, which follows the passive sign convention. So Vx is equal to I34 times 4,000. So that's what we did right there. Okay. Now, next thing we want to do, so we substituted in for I3, so for V34, we did that.
Can't that then simplify the 2000 I34?
Yeah. I mean, we'll deal with that in a second. It would simplify to 2 I34.
Oh yeah. Oh right.
So, but we can go ahead and stick that in there. So this becomes 2 times I34. Yep. All right. Now, what is I34 in terms of the loop currents? We didn't write them all out this time, right? We're going to try to get better at eyeballing it. What loop currents flow through the branch 3-4?
IA.
That's one of them. And IB, right? Which one or both, or neither, do any of them have a direction that agrees with I34?
IB.
IB, right? So we know it's going to be IB, and then plus or minus IA. Is IA the same or the opposite direction?
Opposite.
Opposite, right. Okay, so there we go. IB minus IA. And if we wanted to isolate that according to the loop variables, I could write it like this, just to make it easier to put into a matrix form. All right, now let's deal with C. All right, so C is a little bit longer. C is 3 volts minus V31 minus V12 equals 0. All right. So what substitutions can we make here? There's several we can make. We know that this will be equal to well, what's the volt? So for V12, it's 6,000. So this will be 6,000 times I12, and this will be 2,000 times I31. Right? You see where I'm getting those values from. The 2,000 ohm resistor is there, and then the 6,000. And we just have to make sure we're associating it with the right branch. So then the next thing that we have to do, again following the same procedure, is we're going to make a substitution for the loop currents. So let's go and see what I31 and what I12 break down to. Okay, first though, to make things a little bit easier, let me rewrite the expression. Actually, I'll write it below. All right, so let's start off with 3-1. Actually, let's start off with 1-2. That's the easier one. So what is the current I12? Right, it goes like this. Right? Only one loop current touches that branch. That's IC. And it follows the same direction. So this here is equal to IC. I31. Okay. Looks like that. So we have two different currents that touch this branch right here. We have IC, we have IB. IC reinforces that direction, IB goes against it. Does everybody see that? Right? And again, the Windowpane method helps here a little bit because you can see, right, this branch lies in the middle of two window panes, so I can expect to have two currents. That only works, though, when we define the currents using these smaller loops. We could, again, if we wanted to, have made IC a bigger loop, and that would have changed a lot of the way things were done. So IC minus IB. So what we'll be left with is, and I'm going to move the other stuff to the right-hand side. So we'll have 2,000 IC minus IB. And we have plus 6,000 IC. We'll go ahead and do the same thing that we did above. We will try to move everything such that we isolate the coefficients of the loop currents. So IB, it'll be negative 2,000 IB. And it'll be 6,000 plus 2, so it'll be 8,000 IC. So the two equations that we're going to use to build our matrix are going to be this. If you wanted to, we could add in these terms just to remind you that the IA and the IC, well, all three of them are technically present in both the equations, but they can be represented with a coefficient of 0. Yes? So it all comes down to the math, because when you look at loop C, all right, loop C, the only place where IA would come into play would be here, right? That's the overlap between IC and IA. The thing about it is we don't use Ohm's law at that branch because it's a voltage source. Right? If there were a resistance here, then what we would have is a voltage which would be multiplied by I23, and I23 would be IC minus IA, and that's where it would come into play. But since there's a voltage source there, that relationship is not relevant. So that's the reason why IA doesn't have an effect on that specific part. But it does have an effect on the first loop, right?
Yeah,
For
in that first one, why did you tell them you know that it's 2 milliamps? So why don't you put it in?
Oh, yeah, we will. Okay, sorry, I didn't understand your question. We will. We will. In fact, you know, you're right. We should write it that way to begin with. So what I'm going to do is I am going to, and actually we made a mistake because I didn't really, right, there's still an IB left over here on the other side, which I didn't take into account. I didn't take into account both sides of the equation. So, when we do the final version of this, what I'm going to do is I am going to move IA to the other side. So we'll end up with 2 times 2 milliamps is equal to, and then what we'll end up with is positive 3 times IB, right? This will be moving over here, and this will be moving over there, and this is the actual equation that we need to use. So same thing as we have in the form above, where we have a constant on the left-hand side, and we have a, and we don't really, like you said, we don't need this over here. We have a constant on one side, and we have the variables with their coefficients on the other side. All right, step 5. Someone raise their hand? Yes.
Yeah, I have a question about
Sure.
when you went to like negative 2 times ID minus I, how did you get to like negative 2 times I?
Because of that. Yeah, it's minus IA. You know, this course and electronics, I mean, you have to, the devil's in the details when it comes to the algebra, unfortunately. So, you know, you have to be careful there. Like you can see, I made another mistake, which is I forgot to flip the sign of the IB. It should not be plus 3, it should be plus 1, right? Because we have positive 2 IB, then this will become minus an IB, so it'll be a positive 1 IB. That's when I say for these quizzes and for these exams, it's really important to write down the steps that you're doing. Because, I mean, you know, I'm up here, and it's just as easy to make an algebraic mistake as anywhere else. But, you know, by writing out clearly what it is that you're trying to do, it makes it a lot easier to give partial credit when, again, like I just did, you accidentally add the IB instead of subtracting the IB. Okay, so let's put this into the linear algebraic form. Hopefully I've caught all my mistakes. So this is 4, well, I'll just write it like this. 4 times 10 to the negative 3, and then we have a 3 on the left-hand side. Then what we have is a 2 by 2 matrix because we've taken IA to the other side. So what is the coefficient of IB and IC for the first one? We have a plus 1 and we have a 0.
Why 4 times 10 to the negative 3?
Because it's milli. And then down here we have negative 2,000 and we have positive 8,000.
basically is coming from on this, like for the matrix, like, I'm a little lost where that's coming from.
Is that spot right there? Yeah. Because the left-hand side, the two highlighted expressions are the first row and the second row. And so the first row, the left-hand side is this. All right, so let's show that this works. I'm going to bring up hopefully this online MATLAB thing works this time. All right, so let's try this. What we have is we have an impedance matrix, which will look like this. It'll be 1, 0, negative 2,000, and positive 8,000. Okay, then we'll also have it's not really still the voltage matrix, but the voltage matrix, I don't know why it keeps doing this. Okay. Thank you. Which is 0.004 and then 3. And then so our currents all right, is equal to the inverse of Z times V. All right, so if you look, this is a previous version of the notes. Down here is the solution I got. So 4 milliamps for I2 and 1.375 milliamps for I3. And I1 was, well, so I called them I1, I2, I3. We called them IA, IB, IC. But the numbers, they match up. So this gave us the solution it was that we were looking for. And so I'll just write that real quickly. This is equal to 4 milliamps. This is equal to 1.375 milliamps. And then up top, I'll just sort of include as its own thing up here. We have IA, IB, IC. Now, if you wanted to figure out any of the individual currents, let's say, for example, you were interested in I31, right? Then you would go ahead and combine the loop currents together. So you should know how to do that, because that could be part of the problems, is asking you to move backwards. So let's just do one quick example. So what is I31? I31 is going to be equal to IC minus IB, which is 1.375 minus 4. So it's going to be negative 2.62 milliamps. Okay. And then if you wanted to find the voltage 3.1, it would be that times 2,000 ohms. So you can go either way. You can take the branch currents and work backward to the loop currents. That's ultimately how we're going to solve the problem. But once you're done, you can also take the loop currents and work forward and get the branch currents back. And then that gives you anything else that you might need. All right. So I think, pretty sure, that's the end of nodal and mesh analysis. So this is a pretty big chunk of this class. If you look on the website, under this course. All right, what I will do is I will include on here a link to some of the older lecture notes. Some of the older lecture notes, I don't have them here. Some of the older lecture notes spent a little bit more time on mesh analysis, just a couple of more examples. So I'll post that on the Dropbox if you want to take a look at those. But I really think that there's a reason why I made the change to this format and eliminated a couple of things, because it was really taking up way too much time in the course, and I think it was getting a little bit redundant. Okay, so any general questions on nodal or mesh analysis? Okay, right, this is going to be the last topic that's covered for the midterm. Please make sure that you're doing the homeworks. And you should have all that stuff completed, I would say, by the Tuesday class, right? Because that way you can ask questions during the Tuesday class. We can spend some time going over homework problems, talking about the midterm, and you're not trying to, ask questions like on Thursday evening and stuff like that. Okay? All right. So I'm just going to start the video again since we're doing it different. Actually, let's leave it go. Okay, so next chapter. So the next chapter has to do with operational amplifiers. This is probably going to be one of the sections where you're a little bit ahead of the lecture. I know that you have to use these in ENG214 lab. So I'm assuming you already have some experience with them and at least some understanding of what they do. Can anybody give me a little brief description? What is an operational amplifier? What have you guys done with it? Anybody? You guys have used them in ENG214, right? No? Okay, all right. Well then, I take that back. So an operational amplifier is a device that allows us to amplify a signal. And what it does, how it does that, is it has a set of input terminals, differential input terminals, which will measure the signal. It has sources, external voltage sources that bring additional power into the circuit. And then it has a single-ended output, which is referenced to the ground of the sources. So the symbol that we normally use to describe it looks like this. All right. So we're going to call this our V plus. We're going to call this our V minus. Sometimes you'll also see this referred to as your V2 and your V1. This we'll be calling our VCC plus, okay, and our VCC minus. This is our output here. Okay, so right, these are the signal inputs. This is the signal output. And then these two are your external power supplies. So the amplifier, like any other component, is not going to violate KCL or conservation of power for that matter. The power coming in on both of the input channels can be very low, and then the power of the signal coming out can be significantly higher. And the reason why that can be is because we have additional current, additional power that's going to be supplied by the VCC plus and the VCC minus. This right here is called an open loop configuration. And the reason for that is because we don't have any feedback attached between the output and one of the two inputs. For most cases where we employ an operational amplifier, we use a closed loop configuration with feedback, and that's how we define the gain. There are a couple of isolated cases where we use the open loop configuration. All right, and so how do we define Vout? Vout is equal to a value A naught times, I'm going to say V2 minus V1, which is the same as V plus minus V minus. This value here, if I can drag it out, is called the open loop gain of the amplifier. And this right here so inside the parentheses, this is called the differential input. Right, V2 minus V1. This chapter is a little bit easier mathematically. We're not going to be dealing with really large matrices. We're not going to have problems where there's tons of variables to solve for. In a lot of cases, you're simply going to be given the parameters for the feedback loop, and you're going to be asked to give some characteristics of how this thing works. However, there is an added layer of the theory, the terminology, understanding closed loop versus open loop gain, and just, when I say differential input, knowing what that means. When I say open loop gain, when I say the external power supplies, and there's some more concepts that are going to be introduced there. Okay, next question is and we're going to call these op amps. That's the term that we, the shortened version of operational amplifier. So op amp. So how do we model these devices? This should look familiar. I told you a while ago that there was a type of circuit that we used that was very similar to how we were going to model op amps. And so that circuit looks like this right here. In a second, you'll see there's a reason why I'm using different colors in different spots. Okay. um, so the op-amp model is what is shown in between the green lines. This over here is simply a source. We haven't gone and talked about those too much in depth. This type of source is called a Thevenin source. And then over here is just the load that we are attaching to the circuit. We can also call this I in, we'll call this I out. So the part that's in the blue, we've seen circuits that look like that before with dependent sources. And this is the most basic way that we're going to model voltage amplifiers in the beginning. Now remember, well actually I don't know if probably not remember because we haven't talked about this yet, but there are different types of amplifiers. Okay, there are, well actually no, we talked about different types of sources. We talked about voltage controlled voltage source, voltage controlled current source, current controlled, etc., right? There was 4 different versions. So those same permutations apply to amplifiers, right? You can have amplifiers that generate a voltage and read a voltage. That's a basic voltage amplifier. You can have an amplifier that measures a current and generates a current amplifier. You can have permutations of V and I, and those are called transresistance and transconductance amplifiers. But we're not going to go too much into that right now. Anyway, this is a voltage amplifier. All right, now this may seem like not necessarily the next logical question to ask, but what does the ratio of the output to the input look like when there is no resistor there? When there is no load and we have an open circuit at the output. So for that case, if we use KVL, right, we see that first off, I didn't draw it, so V out is right here. So for that, we have V out is, say it again?
Oh, yeah.
Yeah, V out is equal to A naught V in minus, not equals, minus I out times R out. Okay, when there is no load there, what is I out equal to? Right, how much current is going to flow through an open circuit? No current flows through an open circuit. So that means that this will be equal to 0, and what we'll be left with is V out equals A out times V in. So the, and I can move this to the other side. So the ratio of the output to the input will be equal to the open loop gain A naught when there's no load placed there. And this is just the beginning of the different types of analyses that we're going to do on this. We want to understand how the amplifier works under different conditions. Because we may not be using the amplifier too many times where there's no load attached. That's not a very useful application. However, we can approximate when we have a load RL that's significantly, where the resistance is significantly greater than RO, then we can approximate it as that no load condition.